rotor is controlling that vibration and making sure it's not going to tear the aircraft apart. So you run the thing on the ground and try all the various rotor speeds and combinations of rotor speed and propeller speeds and such like, because the propellers are putting a vibration in, the engines are putting high frequency vibration in, the rotor is taking a low frequency vibration in, and all these start to club together to give various harmonics, and some of these can be quite damaging.
There is still another very great problem that the helicopter had to face, and this was a subject called ground resonance. But it is a situation where, in fact, with the body, the airframe on the ground resting on its undercarriage, which of course is also an elastic entity, and the rotor rotating with blades that were also elastic members, and as the blades oscillated in the plane of rotation, you could get a situation where the effective mass of the rotating system moved offset from the axis of rotation. And if the body oscillated on its undercarriage, then in fact the axis of rotation was moving. As the rotor rotated and its effective mass became offset from the axis of rotation, it could increase the offset of the effective mass of the rotor system. As the offset of the mass increased, well then of course you had a situation where the next rotation it would increase further and further and further until the whole lot disintegrated. And the only way to prevent that occurring was to alter the phase relationships between the dynamical system of the rotor and that of the body.
The resonance testing consisted of measuring airframe response at critical points while varying rotor and engine speeds. Ground resonance was found to have some effect on the aircraft. To correct for this, the original retractable undercarriage was replaced with a fixed and braced undercarriage. One of the major contributions Fairey made to helicopter design was the development of the theories that led designers to be able to predict ground resonance characteristics for a given aircraft design. After the ground resonance tests and reconfiguration of the landing gear, the Rotodyne was ready for its maiden flight. At 22 feet tall and 58 feet long, the aircraft looked ungainly on the ground. But its huge rotor and 46-foot wingspan, covered with the Napier Eland engines, would make it a whole different aircraft in the air. Its military serial XE521 reflected the aircraft's potential for battlefield support roles and the Ministry of Supply funding for the project. A 33,000-pound maximum payload, the capacity to carry some 50 passengers, reflected British European Airways' interest in the project as well. It was on the 6th of November 1957 that the aircraft first took to the air. Test pilots J.G.P. Morton and W.R. Gilackley were at the controls of the compound helicopter. They were prepared to spend the day flying the Rotodyne strictly as a helicopter, the first of its 3 modes of operation. On startup, the turboprops fed air to the 9-stage axial compressors mounted behind them. These in turn pumped air through the tip jets and started the rotor spinning. Fuel was fed to the tip jets and the mixture was lit. Then, with the rotor spinning about 125 revolutions per minute, the Rotodyne took to the air. The flight test plan called for flying the aircraft only in its helicopter mode. After the aircraft lifted off, its yaw control was investigated. Yaw control was accomplished with the Rotodyne by varying the pitch of the turboprop engines. The first flight left all involved confident in the aircraft, and 2 additional flights were made that day. Each of these carried a flight observer in addition to the crew. Originally, the intent had been to keep the altitude of these flights within the ground cushion, but by the end of the day, the Rotodyne was making complete circuits of the airfield at well above the cushion height. The Rotodyne had performed well. The first flights had demonstrated not only the degree of control that the aircraft's engine configuration afforded, but its payload capacity as well, with one flight made at close to its 33,000-pound capacity. Until April of the following year, 70 test flights were made in the helicopter mode. Speeds of 155 miles per hour were achieved, and an altitude of more than 6,000 feet was attained flying under tip-jet power alone. These first flights only covered half of the flight regime for the Rotodyne. It was designed to fly as a gyrocopter as well. In the gyrocopter mode, the tip jets were extinguished, the turboprop engines were disengaged from the air compressors and used for forward flight, while the rotor provided lift through auto-rotation. The area of the flight regime that next concerned the engineers and test pilots at Fairey was the transition between flight as a helicopter and flight as a gyrocopter, and then back again to helicopter mode for landing. In that spring of 1958, the first transitions to and from flight as a gyrocopter were made. These transitions were approached methodically. At first, the coupled rotors were extinguished and declutched one pair at a time, so that the rotor system was stepped from its powered mode into auto-gyration. The transitions had been made at various altitudes, and it was found that the tip jets had relight problems at higher altitudes. This was fixed with compressor blow-off valves that reduced the airflow at higher altitudes during relight. By the end of October, transitions to and from flight as a gyrocopter were being accomplished with confidence in about 30 seconds.
Prior to undertaking public demonstrations, we had obviously explored the characteristics and checked the safety of the vehicle over all of its flight regime. That was in the helicopter mode, forward flight as a helicopter, the transition from helicopter flight to turning off the tip jets to going into the auto-rotative mode, where we then took nearly 50% of the lift on the wing, so that we had proved the viability of the vehicle, and we were then able to demonstrate its characteristics in its different roles.
In the summer of 1958, a redesigned, retractable undercarriage was fitted to the aircraft. This undercarriage used dampers to deal with the ground resonance problem that had been discovered during the ground testing a year earlier. 6 months of flight tests had given the crew increased confidence in the aircraft. The flight envelope had been extended, and transitions from flight as a gyrocopter back to helicopter mode were now being made at altitudes as low as 300 feet. A new paint scheme was applied, and the Rotodyne was ready to begin its public demonstrations. Fairey was sure that the Rotodyne could meet the needs of its potential customers. The airlines by providing service to and from city centers, and the military in battlefield support roles. The aircraft was fast, especially for its size. It had a generous payload capacity and its dual flight mode design lent itself to safety.
There was another nice feature about the Rotodyne. If you were in normal autorotative flight, the normal translational flight, flying along with the tip jets off, and you tried to light up and they didn't light, or you had an engine failure and you knew that you probably weren't easily going to be able to put it in the whole regime, what you could do was you could land the aircraft on a normal run-on landing just like any other airliner. And that's probably one of the big safety features of the whole aircraft, that it could adopt an aeroplane regime. And we did a number of tests doing run-on landings on the airfield, and of course you had the advantage there that you had several shots. It wasn't like the normal helicopter auto-rotation. You could come on the approach, line up, and you could be sent round again and try again, and just land it in that fashion.
Of course, flying as an autogyro enabled the vehicle to fly faster than a conventional helicopter could fly. In fact, the Rotodyne flew at 175 knots back in the 1957, which I think is still nearly is faster than most helicopters fly today.
In January 1959, the Rotodyne established a closed-circuit speed record of just over 190 miles an hour. A helicopter's forward speed is limited by its rotor blades. Forward flight has an asymmetrical effect on the rotor blades' speed in relation to one another. The forward-moving blades are actually moving faster than the retreating blades in forward flight. This difference in rotor blade speed increases with the speed of the helicopter. At a certain speed, the power requirement to move the blades and increased oscillatory stresses on the blades limits the speed of the rotor and the aircraft. These oscillatory stresses are less severe on a gyrocopter, and there is no power requirement at all on a rotor that is in auto-rotation. The Rotodyne was not limited by a powered rotor when it flew in its gyrocopter mode. In June of 1959, the Rotodyne began a publicity campaign with its first international flights. It flew from London's Heathrow Airport to the 23rd Aeronautical Salon in Paris. Stops were made at the Allée-Vert heliport in Brussels and the Issy heliport in Paris en route to the airshow.
There were two sort of attacks on the Rotodyne project, of course. One was to see it as an airliner, flying city centre to city centre. And one of the important demonstrations they did there were the proving flights. One of the things that all